Hello, and welcome back. Today, I want to talk about the lossless impedance matching technique that doesn't require the use of discrete components, but rather cables or PCB traces, or as these are known in a high-frequency environment, transmission lines. What I'm talking about is a specific kind of matching circuit built using a piece of transmission line whose length is equal to a quarter of the used signal's wavelength. So today, I will be looking at the quarter wavelength impedance transformer. If you're curious about what this is and how it works, then keep watching. So, the first thing you might ask yourself is, why? What's wrong with discrete components? Or in this context, lumped elements? Well, any component other than its useful property has some not so useful parasitics. Inductors have parallel capacitance, capacitors have series inductance, transformers have all sorts of problems, and even the humble resistor can run into issues under certain circumstances. However, normally these parasitics are not a concern if you work at low enough frequencies. They do start to become a problem only when your working frequencies become high enough that you get close to the component's self-resonance. Let me give you an example. So if you want to match an 100 ohm signal source with a 25 ohm load using a generic LC matching circuit at a frequency of 1 MHz, you can go with a 9.18 microhenry inductor and a 3.67 nanofarad capacitor. So these are perfectly reasonable components and values. However, if we increase the frequency, say go up step by step up to 1 GHz, we end up needing a 9.18 nanohenry inductor and a 3.67 picofarad capacitor. Now, to give a bit of context on this, a 1206 ceramic capacitor by itself has about 670 picohenries of built-in series inductance just because of its size, and an 0603 RF inductor can have somewhere in the 0.1 to 0.5 picofarads of parallel capacitance. So in certain cases, the component parasitics are close to the actual needed values. This of course does not take into account the inductance and capacitance of the PCB traces and the various series resistances. So as frequencies increase, it becomes more and more difficult to design components and interconnections that have negligible effects. So what can you do when components start to have problematic parasitic properties close to the frequency of work? Well, you stop using components. Various techniques are used in the high frequency range, replacing discrete components with layout elements or other structures. These are also called distributed elements. Today, I will strictly focus on the quarter wavelength transformer. So, it's like a transformer? Well, sort of. It transforms or inverts impedance. This is basically a transmission line that has a specific characteristic impedance, and it allows the match of a source and load impedance based on this equation. And this is valid at a frequency where the transmission line length is equal to a quarter of the signal's wavelength, and no other components are necessary. Now, without going into any of the mathematics, a wave traveling through a transmission line that has a different impedance than the connecting elements will end up partially reflecting at both ends. If the line has a quarter of the wavelength, the first reflection will occur after a quarter wavelength, so the wave will get back to the start of the transmission line after another quarter wavelength, a total of half a wavelength. This condition means that the wave arriving at the beginning of the line will be inverted or 180 degrees phase shifted in reference to the incident wave. Based on this phase inversion and the reflection coefficients at the ends of the line, the final impedance equation is determined. Impedance transformation with transmission lines, to a certain extent at least, will occur with any line length and with any type of impedance. But the nice simple formula only works with quarter wavelengths and real impedances. So the circuit should work quite easily, right? Let's try this out in the simulator now. So for this, I prepared a set of circuits where the signal source has 100 ohms of impedance, and then the load is 25 ohms. So if we run the simulation to look at the various responses, when there is no match, we have a certain level of output signal. When we have a wideband matching, so for example using a discrete transformer, we have a much higher response. So this would be the maximum output signal that we can get in case there is a good impedance match between source and load. And if we take a narrowband matching, say an LC circuit designed for a specific frequency, so 10 MHz in this case, and we zoom in a bit, we can see that this circuit is providing matching at the frequency for which it was designed. Above this frequency, the output signal drops to the level equal to that of no matching. So this is because this is a high-pass filter. And then below there's a strong attenuation because of the filter's effect. Now, if we move on from these examples to a transmission line type matching, first of all, we need to work out the line impedance that we need. So this is the square root of the product of the two impedances that are being matched. So in this case, this adds up to 50 ohms. And then for the line length, starting off from the frequency, we can work out the quarter wavelength, 7.5 meters for 10 MHz in this case. And from this length, we can work out a propagation delay, since this is the parameter that is actually used in the SPICE model, which is 25 nanoseconds in this particular case. So if we look at how this circuit works, we can see that it is providing matching at our desired frequency of 10 MHz, but it's also providing matching at some other frequencies. So it provides a maximum response at 30 MHz, 50 MHz, 70 MHz, and so on. So at all of these odd frequency multiples of the fundamental, it's also matching. The reason for this has to do again with the condition needed to fulfill the requirement that the line needs to invert the signal that is passing through it. We saw this occurs for a line that has a length of a quarter wavelength. But you may also notice that if the line is half a wavelength, so 2 times quarter wavelength, then the reflected signal ends up being phase shifted by 360 degrees, so it becomes in phase with the incident signal at the beginning of the line. In other words, that doesn't really help us. But if we put together a line that is inverting and a piece of line that is not inverting, together they form a line that again generates a phase inversion. So this occurs again for a line that is 3/4 of a wavelength long. And then for other higher multiples, where we have an extra half wavelength segment added on. So 5/4 wavelengths, 7/4 wavelengths, and so on. So for a given length of transmission line, you can determine the multiple frequencies where the phase inversion occurs and see that these are odd multiples. So from the first frequency, you go to 3 times that frequency, 5 times that frequency, and so on. So this is what we were seeing in our simulation. There are a couple more things to analyze in the simulator. First off, the ideal line impedance that we want can be calculated using the formula. However, in practice, we will always have some sort of deviation from this ideal value. Even a commercially available cable can have a few % of tolerance in the specified impedance. So will the matching still work? So if we now come back to our previous simulation, where we had the no matching and wideband matching extremes, we can see our quarter wavelength matching occurring at, well, a quarter wavelength, and then 3/4 wavelengths, 5/4 wavelengths, and so on. And then these minimum points are occurring at half a wavelength and then multiples of that. So now the first thing to compare this to is what happens when the impedance of the line is not the ideal value, but rather either a smaller or larger value, but still within the two extremes. So for that I have a 35 ohm line and a 75 ohm line. If we look at the response of these two, well, we see more or less the same behavior as before. It's just that when we were supposed to be getting a good match, the response is not that significant. So at our half wavelength points, it's exactly the same, but at our quarter wavelength points, it's slightly attenuated. Now, another important case to look at is what happens when the lines have an impedance which is outside the interval of the two impedances to which it is connected. So in this case, I put a 10 ohm line which is smaller than the smallest 25 ohm, which is the load in this case. And I also have a line which is 200 ohms, which is a larger impedance than the signal source, which is 100 in this case. If we look at the response of these two, well, we see a slightly different behavior. So the exact same frequencies are in action as before. These are strictly controlled by the line's length, but the response is different. So at the half wavelength point and upper multiples, we get the exact same response, so no matching is occurring. But at the quarter wavelength point and above, we are getting smaller values. So less signal is passing through than if there was no matching. The phenomenon happening here is that the same impedance transformation is occurring, but now the source impedance is connected to an equivalent impedance that is different from the ideal value. We're still getting the same impedance transformation, it's just that this equivalent impedance that we get is not equal to the source as intended. The greater the mismatch is between the source and this equivalent value, the worse the signal transmission becomes. Now, there are two extreme cases to analyze here. So what happens when the end of your transmission line is an open circuit, and what happens when it's a short circuit? So in these two cases, the interesting bit is not really on the end of the line side, but rather on the signal source side. And for this I prepared a few examples in which the transmission line is terminated in a resistor with a clearly determined value, so 1 megohm for the open circuit and 1 milliohm for the short circuit, and this was necessary to prevent having any sort of simulation errors. So if we run the simulation and we look on the open circuit line, we see the same frequencies are in action, so 10 megahertz, 30, 50, and so on. And at these frequencies, the impedance is inverted, so rather than seeing an open circuit, we're seeing a short circuit. So we see a very small impedance from the signal source side. In a similar fashion, on the short-circuited transmission line, at our quarter wavelength frequencies, we're seeing it as an open circuit. So we see the input signal being unaffected, so it's at 0 dB. Now, there's one more thing to look at here, and that is how does the transmission line's impedance affect the response. So for that I prepared a few more circuits. So in all cases the open circuit is still 1 megohm, the short circuit is still 10 milliohms, and the signal sources all have 50 ohms of output impedance. And for the transmission lines, I have a 50 ohm line, 100 ohm line, so 100 being more than 50, and 10 ohms, which is lower than 50. So if we look at the responses, so this is the 50 ohm line with an open load. If we go to 100 ohms, we see a slightly narrower response, and if we go to 10 ohms, then we see a slightly broader response. So the exact transmission line impedance is impacting the bandwidth of this inversion. In a similar fashion, if we now look at the short-circuited lines, and we just plot out all three of them, so we can see that at 10 ohms this time we have the narrowest bandwidth, and at 100 ohms we have the broadest bandwidth. So one use case for this sort of application is with supply lines. So when your circuit is being supplied from a decoupling capacitor, the equivalent impedance is very small, but you don't really want to short circuit your signal source. So maybe this is the collector of a transistor. So there you can use a quarter wavelength transmission line to isolate the decoupling capacitor from your circuit, so to form part of the biasing arrangement. This brings us to a final question. What do you actually need to get this quarter wavelength impedance transformation effect? An effect that is clearly visible as a wavy response based on frequency and transmission line length. Well, you just need a quarter wavelength transmission line and some impedance mismatch. This is important to keep in mind, since this is one way to diagnose the existence of an unwanted mismatch somewhere in your signal transmission system. So with a perfectly matched circuit, so a 50 ohm signal source going into a 50 ohm transmission line terminated with 50 ohms, if we look at the signals, so at the end there's a flat response, at the beginning there's a perfectly flat response. So in this case there's no mismatch, so there's no reflection. However, if there is a mismatch, first of all, at the beginning of the line, so 50 ohm signal source going into a 75 ohm line, terminated with 75 ohms, on the load side, the signal is again flat, and then on the beginning side, it's again flat. So with this sort of arrangement, there is a discontinuity right at the beginning of the line. Any sort of reflection is going back into the signal source, but you don't really see it if you're looking into the discontinuity itself. However, if we have this other case in which the discontinuity is on the other side, so 50 ohm signal source, 50 ohm line, and 75 ohm load, right at the point of discontinuity, if we have a look, there's no effect observed, so it's a straight line. But if we look at the beginning of the transmission line, here we do see this impedance transformation effect, because the signal being reflected from the discontinuity is visible at the beginning of the transmission line. And finally, if there's a mismatch at both ends, so 50 ohm signal source and load and 75 ohm line, we see this impedance transformation at the beginning. Because of the reflection at the end of the line, we see the reflections at the beginning, and at the end of the line, again we see these reflections because they're coming back from the beginning of the line again. So the reflection is going to the end, to the front, and so on. So we see this different frequency behavior at both ends when there's a discontinuity at both ends. In the end, the quarter wavelength transformer is a widely used tool, not just for very high frequency printed circuit boards, where discrete components are problematic, but even for lower frequency applications where using a piece of transmission line is more convenient than an actual impedance matching circuit. Quarter wavelength matching is used for signal matching, for example, in antenna feeding, but it can also be used in things like supply lines or for signal filtration. There is quite a wide variety of quarter wavelength related structures with multiple use cases. So now to actually apply this principle in practice, if you have a quarter wavelength, say of 1 meter, do you need a 1 meter long cable to perform the matching? No. But that is the topic for next time, when I try out some experiments to apply this principle. But for now, hope you got some useful information after this. Leave your thoughts in the comments. Thank you for watching. Make sure to subscribe to be up to date with all my latest videos, and see you next time. Bye bye.